Thank you for the introduction. I'm Taesoo. I'm currently professor at Georgia Tech and also VP at Samsung Research. Today I'm going to talk about our takeaway from this DARPA AIxCC challenge. Although I'm presenting this is work by a lot of our amazing students and engineers and hackers in our group. And we just won the competitions. Where's our people? Yeah. But most importantly, though, we not just win the competition, we actually won the competition by far. If you can see those presentations, slides, if you combine the four last people, in fact, we score more than them. We are similar to the two other peoples in top three. Okay? Today, I don't have enough time to talk about all these details of our system design, but I hope that I can share some of the lessons that we have. Before we kick off, let's think about one problem, one question. What about we give all these repository that we've been working on and Slack chat histories and some technical report and blog posting all together to the LLM and ask it to create the slide? Or what about we provide all these public information about DARPA AIxCC and ask LLM to create the competitive CRS against us? Everyone think this is not gonna work. But why not? You can think of two different ways. Either our security tasks in DARPA AIxCC either fundamentally difficult, or today's LLM are not yet ready to handle this complexity. But we started our journey as AI skeptics. We thought that those type of security problems are extremely difficult, so that even AGI system cannot handle it. But it turns out it's the limitations of today's LLM. We hope that future AGI system can solve all these security challenges in AIxCC. Dealing with this LLM is more like, today's LLM is more like the Jack and Incredible. I'm not sure you guys watched this amazing animation. The Jack is a superhero. He's born out of two superheroes as a parent, but we don't know what type of superpower he has. But it has a tons of hidden potential. It's speedy, and it has electromagnetism, for example. There's so many different potentials in LLM, but our experience of interacting with today's LLM is more like how to babysit this Jack. Sometimes we can ask it to become a security researcher. Hope that this monster expresses a superpower, so that it really behaves like security researchers. But more than often, it fails. Whenever it fails, we often threatening it. Hey, you really have to work hard. Or sometimes we do cheerleading. Say, what about we give you $10 or $200, so that we hope that this baby monster can perform with these hidden potentials in solving our challenges. We started this competition as AI skeptics, but for reasons. We evaluate tons of different LLMs by ourselves, not limited to the commodity LLMs that we can access to. We also evaluate lots of custom models as well. But at the time, the most of the discussions is more about how to do the prompt engineering well. We talk about, hey, there's a chain of thought or tree of thought or self-consistency. The tiny little details and prompt engineering is emerged at the time. But interestingly, this is the moment that people discovering some magic sentence. This is one of the blog postings from some people. And people discover that if you provide a sentence, they provide a tip, it starts responding longer than expected. But not limited to tipping behavior of the LLM, we start seeing tons of similar properties. Like, we have to do the gaslighting, or sometimes instead of being kind to LLM, you should be affirmative. You can be aggressive about what to achieve out of interacting with today's LLM. And many of the discussions at the time is very primitive. For example, what's the right way to ask to generate the patch? Should we ask unify the diff format as output? Or should we ask complete rewriting of the functions And these are the primitive discussions that we had at the time. We have a lot of discussion about how to express the code, how to include the code as part of the prompt. Should we create the line numbers in front? All these tiny little details actually matter at the time. Worse yet, we realize the context window is probably the fundamental problem. You can think of this way: the training is depending on the quadratic complexity of the context window. We start seeing a lot of racing going on in terms of increasing context window size. We even saw the 1 million token from Gemini at the time, but we got excited. But unfortunately, when you have larger context window, we start seeing some destructive behavior. Like this graph just represented based on the location of the fact, and larger context window size LLM got destructed. You can see some of the error spike is in certain locations of the prompt in this experiment. However, we start seeing some of the potential benefit of adopting LLM in our CRS. One of interesting breakthrough happening at the time is that tons of orchestration engine happening. We first start exploring the Llama index, which nobody using these days. But we start evaluating semantic kernel from Microsoft and LangChain, which is current baseline of our CRS. But interestingly, features like code interpretation happen, which means a year ago, LLM is not good at simple arithmetic. But because of code interpretations, instead of completing token of arithmetic, LLM can start expressing their thought in terms of code. So instead of completing token in formula, they can create the Python code that really calculate the code. We realize it's one of the breakthroughs happening in this space. More than that, LLM now support function call. Now is known as tool call, meaning that whenever they need external dependencies out of their knowledge, we can now start providing external mechanisms as a tool to LLM. We also see some of breakthrough happening in the agentic architectures. One of the interesting experiments like AutoGPT or Baby AGI, or there are tools, very primitive tools like ADAR, OpenDevin, and SWE agent. We realize this is a pretty interesting way to interact with the LLM in this format. But unfortunately though, when we're preparing for semi-final, we don't have enough time. So our stance at the time, we see some potential of adopting LLM, but we minimize use of LLM other than patching. Not because we have small number of credit assigned to us, but we don't fully trust the capability of LLM at the time. Although we apply a lot of LLM for patch generations, but adopting LLM for the first day outperform the state of art of generating patch at the time. But though we extend the fuzzing to adopt LLM in terms of seed generations, and we also reverse the format of the given harness so that we can provide the more structured mutation to the fuzzing process. But after semi-final, we start seeing larger benefit of adopting LLM. One of those things happening in community is that context window size is not the problem anymore because of so many interesting techniques like compacting prompt history or even multi-agent architecture, so that instead of doing all this work in one single context, you can branch off and start leveraging the multi-agent architecture so that we can maintain smaller context window size to solve some of the challenges that we have. Not only that, we now see tons of modern design of agentic architecture, such as Cloud Code and Codex and Gemini. These architecture drastically change our mind in terms of how to design agent in our CRS. So in other words, for the final competition, we adopt LLM in everywhere in our design. This is a design snippet that we extract out of our tech report, which we're gonna share pretty soon. It's a very busy graph, but I highlight some of the components that leverage LLM in our picture. But in the right side, we can see some of the LLM proxy. One interesting design decision we made is that because we have many different CRS running concurrently at the same time, we are not directly talking to LLM services. We have a proxy that provide accounting features of LLM so that we can keep track of how much we are spending in each task. Also, we can provide some of the sandboxing across. We can assign some of the key to individual CRS when we are performing. This is one of the key components that increase the fault tolerance of overall system of the architecture. Let me elaborate some of the design decisions we made for each of those architecture in very high level. Okay? In terms of bug finding module, we adopt the design decisions of N versioning. It means in order to increase fault tolerance of our systems, we intentionally minimize the interactions between CRS. Given a bug finding CRS component, we have 3 different CRS running concurrently. One, what we call multi-lang CRS that support the bug finding features in all sorts of different program languages. But we also have a specialized component for C and Java at the same time. But again, these components are not talking to each other than the C sharing between them. Okay? These decisions are very intentional, so that this is one of the key decisions that increase the fault tolerance during the competitions of our agent. But interesting enough, for each C and Java component, we prepare lots of traditional tools that we are familiar with. For example, in order to implement ensemble fuzzer, we adopt libFL. Unlike many other people just leverage lib fuzzers as their baseline fuzzer, we try to adopt many sorts of fuzzing techniques like libFL, FL++, or we even extend the fuzzing mechanism of Zedger. We also brought lots of custom format fuzzer as well. And all these fuzzing working together to find vulnerability. Not only that, we implement our concurrent executor for each languages. For example, we adopt AIxCC for C. We even implement the concurrent executor for Java from scratch. For directive fuzzer, although a lot of community effort are not concentrated on developing directive fuzzing, but we realize many of the mode that final AIxCC final introduced, such as a Sharif and diff mode, we realize there's huge benefit of adopting directive fuzzer. We also start implementing directive fuzzer from scratch for C and Java component. Because it's the AI competitions, it doesn't sound like very sexy, but these are amazingly well-engineered components that contribute a lot of important roles in our CRS. Let me provide some of the example design decision we made across those components. In terms of Atlantis C CRS, we try to be very risky. It means that we heavily rely on instrumentations. For example, instead of relying on libfuzzer, we rewrite everything in libFL, which is different sorts of fuzzer. And also in terms of provide the directive fuzzer feature, we rely on static analysis that we instrument during the compilation. On the other hand, when we implement the multi-lang CRS, because the fault tolerance is the most important aspect of our multi-lang, so that we minimize the instrumentation during the compilation. It means you build the entire CP given the building script from the organizer, but we place lots of library between so that we provide lots of hooking places so that we can extend the features of libfuzzer without hurting the building process and entire CP. Not only that, in terms of LLM, we minimize the use of LLM in terms of what to tackle in Atlantis C. For example, we leverage LLM for C generations, the input mutation in C versions of our CRS. But when it comes to multi-lang, we apply LLM usage in various components. Not limited to C generations, we implement the blob generations, and we also implement input format reversers. We even build the entire code graph by leveraging LLM. And we also have component to generate the dictionary entry for fuzzing process. Let me highlight some of the design decisions we made in each of the CRS that we designed. In terms of C, one of the interesting decisions that we made is that we provide time-based resource allocation. Many of the interesting design decisions we made for our CRS is per harness space. It means we design an entire system that work for harness in an independent way, particularly in semifinal. But unfortunately, some of the CP has humongous number of harnesses. For example, some harnesses contain more than 30, some CP often contain more than 30 different harnesses, meaning that if we start dividing resources for them, we start seeing some architecture conflict between them. So in order to solve those challenges, instead of allocating entire node per harness, we're gonna behave like we only have one harness that we are working on, given humongous resource per period of time. The entire system just launch for 10 minutes and pause and make a decision to what harness to execute after, based on some of the conditions around the time. For example, given a Sharif and diff mode that have some of the indications of location of potential buggy places, given this hint, we're going to decide this harness potentially do not touch the vulnerability at all, then we're going to completely skip so that we can really concentrate on the harness that really matter to the competition. This component has a lot of benefit. Some of the benchmark in several rounds, we see some of the potential benefit of these time-based resource allocations. For example, one of our CRS that has more than 30 different harnesses, we can literally skip most of them. And then we can just focus on a couple of harnesses that have potential direction to reach the certain places in the Sharif and diff mode. In the C and Java, we also implement the LLM-based input generator, what we call leap-deep-gen. The main motivation behind this is that we realize we can generate the input for the given harness by purely leveraging LLM, but LLM is really slow. So instead of generating input by understanding the code and harness at the same time, what about we generate the code that generate the input for the fuzzer? So instead of directly expressing what we want as an input, what about we let LLM to express the code that can potentially cover many different potential input that it can generate, so that we have a much larger scope that we can cover given a short period of time. And it heavily inspired by the design decision, like deep research, for example, and also ARPA-Evolve that has multi-different agents evolve together to achieve their goal during the lifetime. In the C and Java, we implement our custom version of the directive fuzzer. As I mentioned before, unlike the full scan mode, the Sharif and diff contains some of location that it really matter for the competitions. It basically indicates that these are the places that most important for the competitions. In fact, this is not unrealistic setting. You can think of when you're developing software, whenever you generate the commit, and this is the most important place at the time, we like to evaluate whether this particular commit contained the vulnerability or not. Given this hint, we thought about how to leverage this hint, and we realized the directive fuzzer has a pretty interesting design decision that it can push the directions of the fuzzer a little bit closer to the location that we really care. In fact, there are multiple ways to implement this. You can implement very naive version that you can simply filter out the seed, then select the seed in the right way, then we can hope for the best that it can reach the target location gradually at a time. Or we can implement some crazy component, like we can perform static analysis during the compilation and figure it out what are the important locations during the time. So we leverage the concept of graph centrality, basically indicate that whenever you reach the certain basic block, there's a high possibility that you're gonna reach the other place. We recognize those places all over the places and gradually reach the target locations that we specify during the executions of the directive fuzzer. We start seeing some benefit in terms of time to exposure metrics in given certain benchmarks like Sharif and diff delta mode. We see we can improve the performance a little bit better than the stock AFL++. In terms of multi-lang designed to be language agnostic, meaning that given any other languages like Pythons and whatnot, our design decision should be able to support in theory. If you see the design decision in the fuzzer, there are so many architecture-dependent features in fuzzing. Whenever we see those locations, we're going to leverage the commodity LLM to replace. So instead of relying on language-specific implementation of those features, we leverage existing LLM so that ultimately we can support various program languages at the end. The design of a multi-lang, what we call UniFL, has a crazily complex design decision we made. Well, it's really not meant for you to understand what's happening here, but we're going to provide technical report about that really describe every single component of our CRS later. Hopefully you got some attention on those design decisions today. Let me highlight a little bit of design decision we made for multi-lang. So we have component called input reverser and test lang in order to overcome the challenges of byte-based input mutations of lib fuzzer. Most of the fuzzer are really good at dealing with the binary input format, but you're really bad at handling the structured input. So what about we ask LLM to figure it out, the potential input format first, so that randomly mutate the input as a byte? What about we have a better understanding of the input format ahead of time? This particular component heavily inspired by the competition design in AIxCC that harness has a drastic input space, like standard input, for example, and harness is not explicitly designed to handle those type of input. So first, we have to reverse the how harness handles this input at the first place, and then we have to even, so that we have a chance to execute even further. We recognize some of the challenges in previous design so that we can improve the previous reverse input, the input reversers and test lang to support various problems that we face. One of those problems is that although you can understand the input format, but there is a dependency in parsing those format one at a time. So we can, if you linearly generate or mutate those input without understanding of the dependency between, you ended up modifying some places not even depending on the previous condition. Or we often see some of the state dependency of input. Depending on the environment variable or global variable state, it ended up choosing a very different input format. So all these design decisions are admittedly very fragile. So our decision behind the scene is that although LLM might make mistakes in those, we like to be robust against those mistakes. So instead of saying we heavily rely on LLM, we call this design decision as LLM opinionated. They can make mistakes, but that's completely fine. We have many other components they can handle, can overcome their challenges during the competition as well. We have LLM heavy component in multi-lang, what we call MLLA. It has two different design decisions that we made. There's an MLLA single standalone component that handle the initial bootstrapping of the fuzzing process, so that instead of going deeper into the code snippet, given the harness, we really want to expand the coverage given the harness. Okay, it's a very simple component, so that we don't have to rely on many other LLM usage, but at the same time, we have enough input seed so that we can explore many other components in input harness. There's a separate component, the main component called MLLA, which is really designed to trigger the vulnerability. So instead of generating seeds that are potentially beneficial to the other component of the fuzzer, we really want to discover the vulnerability at the first place by using LLM. So it has components like LLM-based code graph generations or static way to identify the bugs, and given those bug identification locations, what's the best way to create the input that drive entire execution to that location that we identify. So let me quickly describe our agents in patching side. The design principle behind the patching agent is that we like to ensemble all sorts of different agent implementation. And each of the agent has very interesting design decision that is independent to each other. But interesting enough, the patching happened after acquiring POV. And POV can be used as an oracle. It means that if you generate the correct patch, you can immediately know that this given POV can be prevented by this particular agent. By combining all different 6 agents together, as far as one agent can prevent the POV, we can at least choose potentially collect patch as a result of collaborations among them. Unfortunately though, in this larger scale system that we're testing, the building process is really slow. Given after you generate the patch, you have to apply, you have to build everything from scratch, which takes long time. Sometimes we observe some of the executions like over 10 minutes or 20 minutes, which is really hard to scale this our decision beyond 6. So that instead of naively expanding all these agents, we try to limit the number of agents by 6 so that we have enough time to validate and pick the best one out of 6 at the end. Let me highlight a little bit of different architecture decisions that we made. And in terms of architecture, we have a little bit of different architectures across them. And we have different LLM usage and major model that each of the components support. Let me highlight a little bit of design decision behind the scene. One of the components we call Martin, it follows very simple architectures. We divide the patching generation process into 2. We have one component that analyze the fault so that you can do the root cause analysis of given POV. And once you understand, we provide these information to the another agent can naively focus on generation of the fuzz. Martin worked pretty well. In round 3, most of the vulnerability we could discover in C, and 2/3 of the Java benchmark can be discovered by this simple agent. But these are our benchmark suit and how to represent the behavior of our CRS. The green represent we generate the correct patch which prevent the vulnerability at the end. But you can see there are better performing agents like Prism, which is orthogonal to the other agent. But what's important here, if you combine all 6 agents at the end, then at least we're gonna cover all sorts of the benchmark that we have for round 3. The Prism worked pretty well. It adopted the architecture of multi-agent, which is very popular at the time. So you have role of supervisors and multiple team of the agent working together. So supervisors invoke the other agent as a tool, so that we can directly reduce the context window in certain component. But we provide some of the memory across them so that we can minimize the use of the token at the end. Another big decision we made is that unlike other teams, we have custom model. But it's a very small model based on Llama 3.2, it's a 3 billion model, but we perform reinforced learning-based instruction fine-tuning. We adopt the multi-turn GRPO by using the format and soundness, which basically means the correctness of the patch as a reward function. And then we perform online training. It means instead of performing one training at a time, we're gonna perform these generations by using our custom model. We let the LLM, our agent to execute to the end. If as far as we can identify the bug at the end, we can reward the entire model and given process. But because we divide the context window for this, and once we identify the context windows and root cause analysis at the end, we let the custom commodity model to take over at the end. This is a Sharif CRS, but important design decision we make in the Sharif is that when Sharif CRS run against all these repository, provide a probabilistic report of reachability analysis, which other CRS can take advantage of. At the end, we discover 3 zero-day vulnerability. Unfortunately, we didn't have time to apply our CRS to other component yet, other CP yet, but these are the zero-day vulnerability that we discover during the performance of R3 and also internal development phase. In summary, it's a pretty much exhaustive technical descriptions of our CRS, but we're gonna prepare technical report pretty soon. And feel free to check our blog postings and team's website. We're gonna provide very concise summary of what we did in the future. Thank you so much.